Okay, let's take a look at the next four problems. I think these are 22 through 25. These have to do with uh, simplifying radicals, writing radicals as fractional exponents, etc. So for these, something like this, we want to simplify the expression. They tell us to rationalize all denominators. So we want to, there are no denominators, so we don't have to worry about that. Write your answer as a simplified radical with minimal radicands. We want to get as much out of the radical as possible. Okay, so here's how we can think about this one. We've talked quite a bit about this a while ago. We're going to split this into parts. We've got what's under the radical to begin with. Well, we've got the number 18 and we've got an x cubed. And so we want to just get as much of that out of the radical as possible. So first let's deal with the number part. Our answer is going to look like some stuff that's outside the radical times whatever is stranded inside the radical. If we take the square root of 18, we're just going to look for the biggest perfect square factor of 18, which is 9. And so we could rewrite that as the square root of 9 times 2. If we break that into separate radicals, let's put the perfect square, the radical with the perfect square under it first, and circle that to remind ourselves that that's going to simplify to an integer times the square root of 2. Square root of 9 becomes 3. And then we're left with the square root of 2. So the 3 goes outside and the 2 goes inside the radical. Okay, what about the square root of the x cubed part? Let's deal with that. So the square root of x cubed, if we wanted to write that radical with an index, remember that we get lazy, but there's really an imaginary 2 that sits on the radical for a square root. So the index of the radical is 2. If we write that as a fractional exponent, remember that the type of root that it is, which is indicated by the index of the radical, goes in the denominator of the fractional exponent. And in this case, we have an x cubed that's being square rooted, and so the 3 goes in the numerator. And so we could rewrite that as x to the 3 halves. All right, so here's kind of a tricky way to think about this. If we just turn that 3 halves into a mixed number, we could write that as x to the 1 and 1/2. So we'd write that as 1 plus 1/2. Well, the 1 part is the part that's going to be, the x to the 1 is the part that goes outside of the radical. X to the 3 halves is the same thing as saying x times x to the 1/2. And so we end up with an x to the 1 outside. The 1 is, we wouldn't normally write, and you shouldn't write it because it's not simplified if you do, but it's there, right? That's invisible. And then inside the radical, we would end up with an x to the 1/2. Well, we already have an invisible 2 that sits on the index of the radical, so what number goes there? Whatever's in the numerator. Well, once again, whatever's in the numerator. So that would again be an x to the invisible 1. And so what does our answer look like? Well, if we write it a little more neatly then, it would just be 3x times the square root of 2x. Okay, what if that had been, real quick, what if that had been like an x to the 7th inside or something like that? If it had been an x to the 7th, we could write that as x to the 7 halves, which is the same thing as x to the 3 and 1/2. So then that would look like, that's going to give us something like x cubed outside and an x to the 1 inside. So it would be the x cubed times the square root of x. There's the cubed. There's our invisible 1 inside. Okay. Okay, about something like this. Here we're taking a ratio of like bases, of powers with like bases. Remember that when we divide like bases, we subtract exponents. There is a shortcut here, right? Remember that if the top exponent is larger than the bottom, we talked about a little trick where we could keep the base on the top and subtract the bottom exponent. But if the bottom were a bigger exponent, we could save a step by leaving the base on the bottom and subtracting the smaller top exponent from the bottom. Well, it's pretty obvious here that 7/8 is bigger than 1/3, but they are fractions with different denominators, and we're going to have to subtract them anyway, which means we're going to have to get a common denominator. So what if these fractions were closer together and it wasn't so obvious which one was bigger? Then it would make sense for us to get a common denominator so we could directly compare the size of the fractions. Well, what's the least common denominator of 8 and 3? That'd be 24. So we're gonna rewrite both of these fractions in terms of 24ths. So in this case, we'll multiply the top and the bottom by 3, and in this case, we'll multiply the top and the bottom by 8. What's that give us? On the top, we would end up with v to the, multiply straight across, so we get 21 24ths divided by v to the 8. That's supposed to be an 8 there too, remember. Let's fix that. That's an 8 down there too. So multiplying across, we get 8 24ths. 21 24ths is bigger than 8 24ths, so we'll leave the base on the top and subtract the bottom exponent. 21/4 minus 8/24 is just 13/24, and so that's our answer, v to the 13/24. Okay, simplifying something like this, now we're simplifying a radical expression that's got, inside the radical we've got a fraction. Well, first of all, if we could, it would make sense for us to simplify the fraction inside the radical before we even get started, but we can't do that. We can't reduce the 27ths, and we don't have like bases, so we can't combine those in any useful way. So instead, we'll just split this into a square root of the top of the fraction divided by a square root of the denominator. So it looks something like this then. We get the square root of 20x to the 7th divided by the square root of 7y. Now let's whittle these down as much as we can, meaning let's simplify each of these radicals if possible. Well, the bottom one we can't do anything with. There's no perfect square factor of 7, and we just have a y to the first power inside the radical, so nothing is going to come out of the radical on the bottom. And by the way, maybe before we go any further, let's just look at the directions here. It tells us to rationalize all denominators, which means that we can't leave a radical in the bottom, right? No stranded radicals in the bottom of a fraction. So eventually we're going to have to deal with that square root that's stuck on the bottom. But before we do that, let's simplify the top of the blue fraction. So the blue fraction, well, we can do what we did before, right? We can break this into a part that's outside of the radical and a part that's stuck inside. 20, the square root of 20 reduces to the square root of 4 times the square root of 5, and we picked 4 because that's a perfect square. The square root of 4 is 2, and we're left with the square root of 5 stuck inside. We know we can't go any further because there is no perfect square factor of 5. So we get, for the numbered part, we get a 2 outside and a 5 inside. For the variable part, we've got a square root of x to the 7th is equivalent to x to the 7/2, written as a mixed number. That's x to the 3 and 1/2. So we end up with an x cubed outside and an x inside. right, so then we're left on the top with the square root of 5x. So what's next? To get rid of the radical on the bottom, all we have to do is multiply both the top and the bottom of the fraction by whatever the stranded square root on the bottom is. On the bottom, that gives us effectively the square root of 7y squared. When you multiply it by itself, it squares it. And so that cancels the radical. And on the bottom, we end up with 7y. On the top, well, we've got our 2x cubed that's already out front, and then we've got the product of two square roots, and so we'll just multiply the arguments of the two square roots together, meaning we're going to end up with a big square root with the product of 5x times 7y. Well, what is 5x times 7y? That's 35 times x times y. So that's our final answer. How would we check this one? We haven't talked about that yet on this section. Remember that when we're simplifying or rewriting in any way, we're not solving an equation, we would just plug in random values of x and y and then see if whatever the value that the original expression gave us is equal to the value that the simplified expression gives us. In this case, it's unlikely that things would work out well in terms of a number because we're dealing with square roots, but we could easily just turn this into whatever we get for our result into a decimal and compare that to the decimal result over here. If we plugged in, just for example, if we plugged in x equals 1 and y equals 2 or something like that. Okay? Okay. Might be more convenient to pick something like y equals 7 actually, because then you'd end up with a square root of 49 on the bottom, which would be a 7. That would be a little better idea. Okay? So, next. Something like this where we're simplifying the product of some binomials that involve radicals. Piece of cake. All we're going to do here is just distribute like we normally would. If I distribute the square root of x through, I'm going to get the square root of x times the square root of x, which is the square root of x squared, which is x, plus 8 times the square root of x. If I distribute the negative 7 through, I get a negative 7 times the square root of x minus 56. And so when we combine like terms, we get x plus 1 times the square root of x. 8 times the square root of x minus 7 times the square root of x. Well, what does that mean? Those are like terms because that's effectively 8 square roots of x minus 7 square roots of x. That's a total of positive 1 square root of x. And so that's our answer.